Welcome to Module 5, Lecture 18. The most important engineering properties of soils are, and we will come to compressibility and consolidation. The three most important engineering properties are, one is permeability, which we have studied just now. It's an engineering property that leads to the phenomenon of seepage, the flow through the soil. Second is the other important phenomenon or process, compressibility, and associated with this we have a phenomenon called consolidation. Basically, this is same thing as deformation or elastic media. We call it compressibility in geotechnical engineering. This leads to prediction of settlements and what you can call, for all structures, serviceability criteria. How much will the structure sink into the ground or settle, and will it be uniform or will it be non-uniform? Third engineering property is the strength. We call it as shear strength, because soils fail in shear and not through any other mechanism. And this leads to all the stability problems. So we have these three engineering properties. We have done this. Now we will study the effect of load or stress on the deformation of the soil, and later we'll take this up, the third very important property, that is the strength. So when I look at the compressibility, what happens to soil? Let us say the grains are all in arranged fashion here. When you apply a load, if the particles can move along these places, they will try to arrange into a denser arrangement, which means if this is the original thickness, let us say H naught, because particles will now get rearranged into a denser packing, and this difference will give me the compression. Or soil which is occupying a height H naught has become H1 now, and this H naught minus H1 is equal to the compression. So if you look at, even when you walk on the beach or if you are walking on a soft soil, your weight is enough to push the ground below, and your foot will sink into the ground. Why does it happen? Because when you are walking, you are transferring your weight onto the soil, and the grains will try to rearrange themselves. What are the possible ones? In case of granular material, let's say sands and gravel, the deformation is due to three components. One is elastic compression of the grain. The grains may compress. We'll discuss that a little later. The second and the third are sliding and rolling of the grains. So the three components of deformation for coarse grain material are elastic compression, sliding and rolling. Just to illustrate that, let's say I'll take two spheres. You may think of even two steel balls. When you apply the load here, you can see that this contact area is very small. So if I put a force P, if the area is small, sigma is equal to P by A can be very high. You have a very high contact stress, and if you have high contact stress, the strain is equal to sigma by E. E is the modulus of elasticity of the material. So what will happen is these grains will flatten. You can see that the contact area may increase, and then you will have compression, and that is what could be the elastic compression. This distance will reduce, so you will have a slight. So when you have one particle sitting on top of another, and when you apply the load at the point of contact, which is very, very small, just look at this way. If I put two cylinders, the contact area between the upper and the bottom is very small. The diameter may be large, but the contact area will be very small, in which case if the area is small for a given force P, the stress can be large. and the strain will be large, and once the strain is large, the deformation delta is strain into length, so that could be very large too. But in case of soils, fortunately the stresses are not very high. This is very, very small, with respect to one, very small. What we find is the deformation due to one grain, another, it tries to slide. It moves along this direction, or it can rotate. With this as a point of rotation, it tries to, this is sliding and this is rolling. So you will find three components are elastic compression, which is negligible, and sliding and rolling of the grains with respect to another. So here is another example. I have one grain resting on it. When you apply the load, this grain may try to move, that is sliding, or it can rotate, which is rolling. So these are the three most common deformation mechanisms in case of sands. In case of clays or fine-grained soil, silts and clays particularly, we know that clays are plate-like particles. So this thickness T and the diameter are very different. D can be 10 times to 100 times the thickness. Very thin, it's something like, let's say, if I look at this particle or the phone, the thickness is only hardly about 8-10 millimeters, but the length is maybe 10 centimeters, 12 centimeters. So you can see the ratio between the thickness and the size or diameter could be very large. I mean, diameter to thickness could be very large. In that case, we also looked at the particle arrangements. These are all how the clay particles will look in nature. So when you have plate-like material or particles, the deformations are due to 1. Plate bending, 2. Plate rotation, and thirdly, squeezing of water, absorb water. So we'll see how these mechanisms appear in case of fine-grained soil. Let's visualize there is a coarse-grained material, another coarse-grained material, and clay particle is here, another coarse-grained material. If the load is acting on the upper coarse-grained material, the plate may bend. So this is plate bending. Whereas if I have fine-grained soil alone, and if I am applying a load on top, these particles may rotate. So a particle which is inclined at this angle may, for all you know, rotate to this direction. If all of them do that, you will have compression. So this is due to rotation of particles, clay particles. Please remember, the mechanisms we are talking are only for fine-grained soil. We also said that a clay particle will have adsorbed water. This is, and this is the clay particle. So if I have another clay particle here and you apply the load, they try to come closer to each other. They may squeeze out the adsorbed water. So when the water molecules which are attached to the clay particle, they are squeezed out, again the particles will come closer to each other. Initially they are at a distance of, let's say, 100 angstrom. They may come down to 80 angstrom. That will lead to deformation. So the three phenomena that contribute to deformations in fine-grained soil is plate bending, rotation of clay-like particles, plate-like particles, and squeezing of adsorbed water. Over all these things will contribute to the overall deformation. And please remember, there is nothing like a pure granular material or pure fine-grained material. You may have a combination, in which case all these mechanisms will contribute to the overall deformation of the soil. Then there is another very interesting aspect in terms of deformation. We have a large area, let us say 100 meters by 100 meters, and I am trying to increase the load by building a embankment or whatever it is, 5 meters. Say the unit weight of this material is 18 kilonewtons per meter cube, and here is the soil, clay stratum or whatever soil stratum, this thickness H and the width we are talking of the loaded area. If I look at it, if B is, this is hard stratum, I am not worried about its compression anymore, it is a hard rock. This is what you can call a compressible stratum. If B is greater than H, H may be 5, 10 meters, maybe 15 meters, but B is 100 meters, 200 meters, etc. You are on a coastal project where you want to reclaim, let's say 1 hectare, which means you are talking of something like 1000 meters by 1000 meters, and you will bring in some soil, put it on top and raise the ground level. If that is so, what kind of deformations occur in the central portion? I am not talking of the edges, but I am only looking at, let's say I am looking at this point inside. When you are applying the load, most of the soils would try to, if I am applying, you know from theory of elasticity or simple mechanics, it has a tendency not only to compress but to expand laterally. This is what you call a simple elastic deformation. If I take a small cylinder or a cube in the lab, if I apply force or a stress, you will get compression in the direction of the load, but lateral expansion because of the properties of the material. You have compression in the direction of loading and expansion. But can it happen in the case of a large loaded area? Please remember, we have one element here, there is another element here next to it. If it has a tendency to expand, what happens to the neighboring element? It also wants to expand. So they cancel each other because each of us cannot expand. So you compress, or both the elements are compressed, and you have what is called as one-dimensional compression. What it means is all the deformation is only in the vertical direction. There can be no lateral deformations. So epsilon z is not 0, but epsilon h is 0. If you have a very large loaded area where B is large compared to the thickness, you will find the same. Let's also look at even simple an embankment on a clay layer. You want to construct an embankment, and here is a compressible layer which is only about 4 meters thick. This could be maybe some 40 meters, and if I look at this layer now, the thickness h is much less than the width we are talking of. So again, this layer will compress only one-dimensionally. In geotechnical practice or in civil engineering, there are many situations where the deformations are only in the vertical direction and lateral deformation is 0. Because if I take an element, it will like to expand, but the next element also wants to expand. So they try to push each other and prevent lateral expansion, leading to one-dimensional compression. We have the other two also in practice. I have a two-dimensional deformation. I have here a strip footing B, and the deposit H are of the same order. B is approximately H. When you apply the load here, you will find that compression is possible, also lateral deformation. It's compressing and tries to move outward, except of course along the center. All other particles will have two deformations. So you can have vertical deformation and lateral deformation, or I can say vertical strain and you will have horizontal strain. This is called a two-dimensional deformation problem or situation we meet with in foundation engineering, etc. We also can have a two-dimensional axisymmetric one. For example, if I have a circular liquid storage tank or a water tank and you are applying load here, and here is the deposit. Again, this diameter d and this thickness are of the same order. H is of the same order as the diameter. In this case, it's not just lateral, it's radial. So you can have deformation vertically and of course radially. So when I'm looking at the plan, the deformations can be in all directions. These are called a circular loaded areas. Now it can be liquid storage tanks, even footings, etc. They are called axisymmetric problems. You will have vertical strain and radial strain. Please remember, when you are applying the load, something like this, if you are applying load on a circular area, not only the deformation will be downward, but it can be in all directions within the plane of the deformation, that is the horizontal plane. So these are called the axisymmetric problems. And lastly, the most complicated one is under building foundations and special situations where you can have a three-dimensional deformation. You have a rectangular footing on the surface which is being acted upon, and then you will have not only epsilon z, you can have epsilon x and epsilon y. So if I have, for example, a footing of this rectangular shape and you are putting a load here, you will have deformations in the vertical direction, you can have deformation in the longitudinal direction and the deformation in the transverse direction. So this is a real three-dimensional problem. This is a rectangular footing or any irregular shape you can put in. You have three-dimensional deformation. So finally you can say in practice you can have 1, 2 and 3-dimensional problems. Please remember that, but we'll only study here first the 1-dimensional problem, which was started by Terzaghi. Even though earlier the method was discovered or innovated, you can have 1, 2, 3-dimensional compression. Let's only concentrate on 1-dimensional compression. In order to do this, we need to take a very small sample. So I take a steel ring. The thickness is hardly maybe something like 25 millimeters. Usually we have 20 to 25 millimeters, and the diameter could be 50 to 75 millimeters. You put the soil here. You can prepare a sample or push the ring into the ground and get it. You put in a small porous stone. We put another porous stone on top. Oh, I should mention, we also provide a small filter paper. We also have a filter paper. Can you tell me why we need a filter paper? So that the particles will not come and block the pores in the porous stone. We don't want to lose any soil, so all the soil will be here, and filter paper will prevent migration of particles from inside the sample onto either the bottom porous stone or the top porous stone. And at the top we put in a small ball so that there is no friction, and we apply a load P. So if I divide P by area of the sample, I get the stress. And when you apply the stress, naturally there will be compression. So by applying the load, I am deforming the soil and try to measure it. How do we measure it? I put a dial gauge here, which rests on the top platen. So when the soil gets compressed, the dial gauge gives me the deformation. It's a very simple test. The actual equipment is called odometer, but for some historical reason, this is called a consolidation ring or apparatus. Consolidation test, you can say any one of them. This ring is usually made with steel, so its E is very high. So if I have a steel ring and if I apply the load, what are the chances that it will expand? negligibly 0, because E value is 210 gigapascal, and we are not talking of high stresses. In soils, we talk of only maybe 100, 200, 300 kilopascals. So we don't have that level of stress to deform the ring. So can I now say this ring will make sure that there are no horizontal strains? Please remember, in all these tests, epsilon h is 0. There is no lateral deformation, there is no lateral strain. Because of that, this will simulate the one-dimensional compression we are interested to study in the field. So a odometer ring or a consolidation test apparatus will give me one-dimensional compression. What we do is initially we put a seating load sigma, let's say of the order of something like 5 kPa. Then we increase it to, let's say, 12.5, 25, 50, 100, 200, 400, up to something like, let's say, 800, 1600 kPa. This is called increasing by doubling the load. So from 12.5, I go to 25. So whatever is the load, I double it, and then I take the compression. Now, in case of soils, the compression is not necessarily immediate. So I have to take readings with time. So 0, I take 15 seconds, 1 minute, 4 minutes, 9, 16, 25, 36, 49, 64, 81, 100, maybe 400, and then we go for 1 day, which is 14, 40 minutes. You can immediately see that these are all squares of the numbers, 1 minute, 4 minutes, 9 minutes. If you want in between, you can have 2.25, 6.25, 12.25, or you can have 20.25, etc. But after a certain stage, you don't need to worry about it. Why? Because the settlements in case of soils are not immediate like in case of steel, concrete, or any other material. Here you have grains which are trying to roll and adjust. Plus there could be water. If there is water within the sample, water needs time to go out of the sample, and that is why we provide the porous stones. You allow the water to go, but you do not allow the soil particles to move out of the sample. Now you know the permeability is a very low value. If permeability is low, obviously it takes time for the water to come out, and that is why usually this consolidation test takes each sample we load under a given load for 1 day. Maintain the load for 1 day. So if I plot it, I'm plotting time here and the load, etc. Whereas if I now look at the deformation or compression, again time, you will find that it goes on like this. What you notice is the deformations increase initially very rapidly, but over a period of time they become small and negligible. So if you wait for 1 day, which is equal to 24 hours into 60 minutes, that gives me 1440 minutes. Usually you find that the settlements are more or less over. In case of sands, whose permeability is very high, you will find that the deformations are over much faster. So if I plot the time versus deformation in case of sands, you can say usually in case of sands about 30 minutes is enough, unlike 1 day for clays, silts, etc. So this test usually in case of clays runs to about 2 weeks, whereas in case of sands I can finish it faster. After I reach the maximum load of 1600 kPa, we had to unload it. So this time I do it faster. Previously the load increment ratio is 1. That means the increment is equal to the load, and now I find the decrement is 1/4. From 1600 you come to 400 kPa, from 400 you come to 100 kPa, 100 to 25, and 25 to you can come down to the seating load 6.25 or 5 kPa, whatever it is. So what you then do again would be there will be slight this one come back, and you will find that there is a slight recovery. Soils being inelastic, even if they compress by about 5 millimeters, the recovery would be less than 1 millimeter for this sample. That is because once the grain goes into a lower position, it will not bounce back. Elastic compression, yes, you know that elastic means these deformations are recoverable. But when you have sliding and rotation, obviously it cannot slide up. Anything that moves down, imagine you have a slope and a particle has gone down. How can you expect it to move back just because you removed the load? There will be friction again, and the same thing would happen in terms of rolling also. It has come down to a more stable position, it will not roll back. So usually soils are inelastic. So if compression is say delta C, on unloading the recovery delta E is very small, is of the order of usually 5 to 10% only. Maximum it can go to 12%. So what we do is all the deformations are measured through this dial gauge reading. So if I know the thickness H0, say dial gauge readings are, we have an accuracy of something like 0.1 millimeter, T is equal to 0, the dial gauge reading is say 10.0. So 1 minute this can become 9.85, 4 minutes 9.64, 9 minutes this could be 9.32, 16 minutes is 9.15, 25 minutes is maybe 8.98, etc. That's how the readings will be on the dial gauge. And so I can say compression is equal to 0.15 millimeters, and here is 0.36, 0.68, 0.75, 102, etc. in millimeters, let's say. So you can plot with respect to time how much settlement is taking place, and then I'll take the final settlement. This could be after 30 minutes in case of sands, or after 1 day in case of clays. This is for coarse grain material, this is for fine grain material. So let us say we increase the load from say 12.5 kPa to 25 kPa. So can I say the delta sigma is equal to 12.5 kPa. On the sample, you have increased the load from 12.5 to 25, and then you have put the dial gauge, which gave me the reading of, let's say, 1.1 millimeter. This is the final compression. That means dial gauge reading at T is equal to 0 minus dial gauge reading after either 30 minutes or 14-40 minutes. That gives me the compression. So let us say it's equal to delta S. The thickness of the sample is H. So can I say the strain is equal to compression by the thickness, or H0 if you want to put it that way. This will be the vertical compression. Is there any horizontal deformation or horizontal strain? We said this is made of steel. It's a steel ring. So epsilon H is 0. So what is happening to the volume? Initially, let's say the area of the ring is A. Can I say that volume is equal to area into H0? Similarly, volumetric compression is delta S into area. How much volume has it decreased? It decreased by, this is delta S. So the amount of decrease in volume is delta S into H0. Can I say volume decrease delta V is delta S into area. So what will be the volumetric strain? If I say epsilon V is the volumetric strain, this is equal to delta S into A by H naught into A. What is the initial volume? H naught into area of cross section, and by how much does it decrease? It decreases by delta S, and so delta S into area gives me the decrease in the volume of the sample. Can I also write it as change in void ratio by the initial volume? When you have a soil which is consisting of solid grains and voids, what is that which will decrease? Do the grains decrease in volume, or only the voids will decrease in volume? We said the grains are very, very incompressible. We always take it that way. There is no elastic compression. Okay, which means whatever volume change is taking place, it's only because change in void ratio. Now, can you now relate this vertical strain to the volumetric strain? As you have seen here, epsilon z is delta S by H naught. You are writing it as delta S into area of cross section, H naught into area of cross section, which is equal to the volumetric strain, which is equal to change in void ratio by the initial volume. If I know the unit weight of the soil, I can find out the initial void ratio, and if I know the void ratio, I can get the denominator. So here is one simple way. Now, can I calculate delta E is equal to delta S into 1 plus E naught by H naught? I can find out what will be the change in void ratio due to this increment. What is the increment? From 12 to 12.5 to 25 kPa. So, if I start with initial void ratio, for each subsequent one, I know what will be the change in void ratio with each load, and you can plot void ratio versus the effective stress plot. So, what we do here is E versus, so at a seating load of, let's say, something like 5 kPa, I have E naught, and then as you increase the load, you get different points and you get a curve here, and when you unload, you find that you get a much flatter curve. What you find now, very interestingly, is that the loading gives me very large compression. As the load is increasing, this is up to, let's say you've gone up to 1600 kPa. Void ratio here was maybe 0.85. It will come down to 0.42 or something. So, as you increase the load, void ratio decreases, and unloading will give me only very small recovery. So, what you find here is a simple change void ratio versus linear plot with effective stress, E versus sigma prime. So, that is how we do the test, and if I take the slope of this line is called A sub V, coefficient of compressibility, is nothing but change in void ratio by change in effective stress. So, when you increase the stress, the slope, we are trying to linearize it, and the ratio of change in void ratio with respect to effective stress is called the coefficient of compressibility. Did you notice one very interesting feature of this curve? As you increase the load, the curve is becoming flatter. Why does it happen? Here, when I increase the load, I get large compression, but for a larger increase, I don't get even that much of compression, less. What's happened is that the particles are packing into a denser state, and if they're all already in a dense state, further compression will be less. So, let us say from 0.85, it has come to 0.5. Obviously, when you have void ratio of 0.5, there are very little, very relatively smaller amount of voids, which will not allow you to allow the particles to get any more closer. So, what is happening is, in case of soils, as you increase the load, the soil becomes denser and denser, and the deformation becomes smaller and smaller. So, if I look at AV here, and if I look at AV maybe after the final value, the coefficient of compressibility at the larger load will be very small compared to the initial value. So the soil is becoming denser and stiffer with increasing load. We'll now try to define these parameters in the next